Now we're going to talk about reasoning, and specifically in this lesson we're going to talk about inductive reasoning and what a conjecture is. So we're going to start off with a conjecture. Now a conjecture is nothing more than an educated guess. So when you look at something, you can look at it and make that educated guess about it, and you are making a conjecture. Inductive reasoning, that's when you come up with a conjecture based off of a bunch of examples. So you see, some numbers maybe, and you can predict what the next one is. And we're going to look at some examples of inductive reasoning, and you're going to come up with a conjecture. Now, my suggestion on many of the slides for this lesson would be for you to push pause and see if you can come up with conjectures based on the problem. Now, in this one, there's two different ways to make your conjectures on how many dots will be in the next picture. My first one, when you look at here, would be the geometric approach. Now go ahead, push pause, see if you can figure out how many dots will be next. Now, geometrically speaking, I would just look at my pictures and I notice that it looks like I'm gaining another row on the bottom each time, and that row is gaining a dot. So my last one had 4. So this one's going to have 5, and then just continue the pattern up. And then I could count the dots. So bottom row I have 5, plus 4, now I'm at 9, plus 3 I'm at 12, plus 2 I'm at 14, and add 1. That would tell me that there will be 15 dots in the next picture. Now we could also look at it algebraically. Now the way you look at it algebraically is you pretty much ignore what the picture looks like and just look at how many dots are in each one. So in the first one we have 1, and then we have 3, and then we have 6, and then we have 10. And somehow we got to come up with 15. So you kind of have to ignore the 15 for the time being. But what I notice here, when I go from 1 to 3, I added 2. This is one way to look at it. When I go to 6, I added 3. And then when I go to 10, I added 4. So my conjecture would be I must have to add 5 next, because it's going 2, 3, 4, and then if we add 5, what do you know? It works. We end up at 15. So the geometric approach would tell you to draw a picture. Algebraic approach would say let's look at the numbers and see if we can come up with a pattern. See if we can make a conjecture on this one. And again, I would try to push pause, see if you can come up with what the next number is in this sequence of numbers. The way I look at this one is I notice I have a bunch of fractions except the very first one. But what I'm going to do is I'm going to turn that very first one into a fraction of 1 over 1. Because now it follows the same pattern that all the rest of them do. We have a fraction. And then my conjecture is going to be that my next number is going to have a 1 in the numerator. Every other one has a 1 in the numerator, so the next one must have to have a 1 in it as well. And then I have a couple different ways I can look at this. I can look at it kind of like I did with the last one. This goes up by 3, and then by 5, and then by 7, and then by 9. So my conjecture, my educated guess would tell me that this must go up by 11, and if it does, I'm going to end up at 36. Now another way to look at it would be I can look at this first fraction as 1 over 1 squared. The second fraction as 1 over 2 squared. The third fraction as 1 over 3 squared. And then it's 1 over 4 squared and 1 over 5 squared. So my conjecture as I go to this next one would be, well, just like I said at the beginning, the numerator is going to be 1, but my denominator is going to be 6 squared, because when I look at all my denominators, I just went 1, 2, 3, 4, 5, and then I have to square it. Well, if I square 6, I'm going to be right back to here. So my educated guess, or my conjecture, is that the next number is going to be 136. Here's kind of a fun one. This goes back a few years, but we have some math symbols. We have a singer, and we have a stage. Some of you may remember, but for brings up my conjecture would be, well, we have the math department, a little pie ditty, lose yourself in the digits. Sometime I'll play the song for you if you've never heard it. Now here's one that's a lot of geometry involved in this one. We have 3 different points. We have point L, point M, and point N. And then it tells us the length of segment LM is 20 units. The length of segment MN is 6 units. And the length of segment LN is 14 units. Now please start to get in the habit of properly reading it. Notice the way that I read this. Length of segment LM, length of segment MN, and length of segment LN. I never just said LM equals 20. I said the length of the segment because that's what it's saying. Now we want to make a conjecture and draw a figure to illustrate your conjecture. So I have to come up with something based off of that first line up there. Well, I have 3 points. Where they're exactly at, I don't know yet. Maybe they're linear. Maybe it looks like this. Let's see if that will work. So if I do this, now it tells me the length of segment LM is 20, and that looks like the longest one. Now if I did that, that would tell me that L would have to be here, M would have to be here, and then looks like N would be in here. Now, does it work though? Well, it tells us from M to N, tells us that this part is 6. It tells us that from L to N, or the length of segment LN, oops, that's not what I wanted there, not the color anyway. I'm going to do that. The length of segment LN, that is 14. And it tells us the length of segment LM, at the very beginning, that was 20. And I look at this, well, if my whole segment is 20, it would make sense that the 2 pieces would be could be 14 and 16. They could be. Now, they don't have to be, but in this case, it's telling us that that's the given information, so I know that much. So then my conjecture would be, I have multiple conjectures I could make. I could say that N is between point M and point L. I could have also said something that's not quite as specific. I could have just said point L, point M, and point N are collinear because they're all in the same line. And I would have my conjecture. Now some people would say, well, Mr. Rude, why don't you try putting those points so that they would not be on the same line? So maybe go like this. So here's L, maybe here's N, and here's M. Now when you do this and put it all together, well, this part from L to N, that still has to be 14 because that was given information. The distance from N to M has to be 6, and the distance from L to M has to be 20. And we look at it and go, well, could that work? I mean, it looks like it does. I could say that my points are non-collinear. I could say that they make a triangle. But if we start to think about this, that's 14 and that's 6. Could I really have them create this angle at N and then this part really be 20? And the answer is no, it would never work. You can't get a triangle to form using a side of 14, a side of 6, and a side of 20. And that's something that we will take a look at more when we get into our chapter dealing with triangles. So take this example and totally ignore it because it will not work. So you can go with point N is between point M and L, or you can go with points L, M, and N are collinear. Now, a counterexample. Counterexample is nothing more than an example that's going to prove something wrong or prove something to be false. So if you can come up with one example and one example only that proves something false, you've come up with a counterexample. And really, it only takes one example to prove something false. There might be a million different examples that will prove something true, but if you can find one that proves it false, you say the whole statement is false, and you've come up with that counterexample. So here I have one of those examples where I want to come up with a counterexample to prove this false. So we have this table. on unemployment rates for various cities in Kansas, and we want to come up with a counterexample for this following statement. Now the statement is right here. It says the unemployment rate is highest in the cities with the most people. So basically what that tells me is if I were to arrange all of the populations and then look at the unemployment rates, my biggest population would have the biggest unemployment rate, and as the populations went down, the unemployment rates would go down. But apparently this is a false statement because somewhere in here we should be able to come up with a counterexample. Now what I'm going to do is I'm going to look at Shawnee. Highest population of what I have here, largest population. The unemployment rate is 3.1. So what I need to do is I need to find a city that has a lower population but a higher unemployment rate. And what I'm going to do is I'm going to come down here to Douglas. Douglas has less people, but notice higher unemployment rate. And that goes against what my statement said. So I have come up with a counterexample. My counterexample would be look at Shawnee and look at Douglas. Their populations and unemployment rates don't match what it said in the conjecture up here. Now here's another one. And again, push pause and see if you can come up with a counterexample that would prove my conjecture false. Now remember, you're trying to prove this false. Now in this one, I look at the given information. It tells me that if I have a number m and a number y and I add them together, the sum of them is greater than or equal to 10, and I also know that my y value has to be greater than or equal to 4. My conjecture then that I came up with was, well, m has to be less than or equal to 6. But I can come up with a counterexample. And my counterexample would be this. Well, we already know that y has to be greater than or equal to 4, so I'm going to start there. And I'm going to say my y value, let's just go with 4. Now, I know that when I take m and y and add them together, it either has to equal 10 or it has to be greater than 10. So to help me come up with a counterexample, I'm going to say that m equals 7. So now, ignore the red for the time being, because that was the conjecture that we'll say that I came up with that we're trying to prove false. If I look at what's the very first part, it tells me that m plus y has to be greater than or equal to 10. Well, 4 plus 7, yep, that's greater than or equal to 10, so that's good. I come over here, the y value has to be greater than or equal to 4. 4 is equal to 4, so that's good. So what I've done is the given information I've satisfied, and that's what you have to do. Now, the conjecture part, though, that's the part that you want to prove this false. You want to come up with a counterexample, something different than that. Well, did I? Yeah. This says that the m value has to be less than or equal to 6. I found something that's greater than 6. Therefore, y equal to 4 and m equal to 7 would be a counterexample to disprove the conjecture in this problem. In my next one, this one I have 4 points, point W, X, Y, and Z, and my conjecture says that those 4 points are collinear. Well, could they be collinear? Yeah, I could go W, X, Y, Z, just like that. Now, here would be an example that would prove it, not necessarily prove it true, but it's an example of where it would actually work. But what I'm trying to come up with is, I'm trying to find something that disproves this. Well, what I'm going to do for that is I'm going to say, well, I could put point W here, I could put point X here, I could put point Y here, and I could put point Z here. Now I have my 4 points. That's all it tells me that I had 4 points. It doesn't tell me where they have to be, but I made them non-collinear. So this right here is a counterexample to disprove that point X, point Y, and point Z would be non-collinear. And there's the lesson on the beginning of inductive reasoning and conjectures.